Hello and welcome back to the next lecture of the session, Laser and Contacting. I'm here with Mr. Dr. Sedmair. He will speak about a beginner's guide to making battery modules to wire bonding. A start need not to be hard. He's from FS and Bondtec. And before we begin, a few hints. You will find the recording of the session afterwards. And if you want to have the handout of this presentation, please contact Dr. Sedmair at the booth of FNS, and he will be kindly help you with your request and give you the slides. Furthermore, please ask questions through the tab questions, and we will be welcomely answer them in the short Q&A session after this lecture. And now the stage is yours. I give the word to you, Dr. Sedmair.
Thank you, Michelle, for the introduction. And good afternoon, everybody, and welcome to our very short tour d'horizon of how to get started in making battery modules, at least by wire bonding, and why this doesn't have to be difficult. A very brief overview. Who are we as a company and where are we? What do we do and what can we do for you, both in terms of equipment, but also in terms of services beyond the equipment? Well, who we are a company based in Austria. This is unfortunately not quite the look out of our window, but we are close to Salzburg, about 45 minutes away from Salzburg and a bit over an hour from Munich, so we're easy to reach. We are a small family-owned company with about 40 employees, but we already have something like 40 plus years experience in making wire bonders. So we're quite an old hand in the business. Here is basically the entire company, and the person in the middle with the red tie is the general manager and owner of the company. Okay. What do we do? Well, battery modules are very often made up of small cylindrical cells of the 18650 or 21700 type. Those are the cylindrical cells that we are focusing on and that we will be speaking about later. Obviously, to make a module out of these individual cells, they need to be connected electrically, and that's the equipment we make to do this. Here is a typical battery module made up of about 40 cells. So this could be something like in an electrical lawnmower, or it's a little bit too large for a pedelec, but all kinds of different power supply usages are thinkable for something like this. To connect those electrically, we propose wire bonding, obviously, because this is the business we are in. And what this looks like is shown on this video. I hope you get a smooth video recording shown here. What this machine does is it's almost a little bit like a sewing machine. We push down, make a wire connection to a second point and cut off the wire. And in the short times where this bond tool, as we call it, pushes down, we actually make the welding connection to, in this case, the battery top. That's the bonding step, as we call it. Now, why are we so fond of wire bonding? Well, it's extremely flexible because you do not need a prefabricated connector of any kind. We just use the wire or the ribbon in whatever length and whatever orientation you need it. So you don't need to prefabricate something. You just program the bonder to go from spot A to spot B, wherever that is. So if you have a different module to make, or the design of your module changes, and those are typically things that happen as you start out when you have to make very small sample quantities. All you do is you reprogram the bonder. You do not need to wait for extra parts or something new. Another nice thing is the machine and the process are extremely tolerant to variations in the position of the cells or also in the height of the cells, because the bonder will simply react to that by itself. And you can do something. What we see here is a chaining process. And as you can also see, we do not only connect a few cells in series, we can also make more than one wire, depending on the kind of current we want to conduct. So this is all very straightforward. You can even do things like making the second bond on the top side on the cell rim as well. So you can bond both poles on the same side of the module. And that is interesting because you don't have to flip the module around once you start it. You can also make a fairly low module because you only have connections sticking out on the top side. And the entire rest of the cell body is free if you want to do some kind of cooling or other thermal management. So that gives you extra design flexibility. In a case like this, where you can see another module that we've shown here, we have the two connections from the plus pole and an extra connection from the rim to a plus pole, as you can see here. So here you see the bond running from the rim to the neighboring plus pole. And of course, here we have a much smaller area where the bond has to go on the rim, and the rim is in addition bent and curved. But we can get around this problem because we have a pattern recognition unit in the bonder that allows us to locate the bond position very, very sharply and very precisely on the rim of the battery cell. In fact, if you look here on the left, you see the camera image from the bonder itself that shows us just what we are doing and where the bond itself is being located. So we can even bond, of course, outside the cells. We can bond to bus bars without any problems, or we could tie in additional circuitry like a battery management system that does not have to be at the same level. And here, as you can see, we can bond outside to a bus bar that will take the current off these plus poles. And you see we're making 2 wires each to get more current through. A battery management system could be at a higher level above the battery cells. That's also no problem for a wire bond to get to. And again, no matter what the connection is, you could make whatever the bonder can reach, you can bond to. Here you see a different type of battery cell module where we have only bus bars to connect to and not cell to cell, but bus bar. That's just a question of the design you like to use. I was talking about the currents you can carry here, and indeed, if you use an aluminum wire, which is kind of a standard, most frequently used, of about 400 microns diameter, you have a fusing current of something like 20 amps in this case, and as you can see from the diagram to the left, this could be higher if you use different types of wire, such like copper or copper core type of wire. Typically, of course, you would derate the current well below the fusing current. So in our experience, a lot of people use something like 10 or 12 amps for a typical 18650 cell. Obviously, if you want higher currents, you could use different materials. As I said, you could also use ribbons, or of course, the simplest way is simply to make more than 1 wire. 2 wires is actually quite frequently used, and that gives you the typical 20 or 25 amp current rating that you may need. Now, a little bit more about the technology. What's so advantageous about wire bonding and why is it so useful? Well, technically, it's a welding process that happens in the solid phase, and it's happened by friction. So the crystal lattices of the wire and the substrate are brought into atomic contact and form a metallic bond without any molten phase. That's the important thing to remember. The connection quality is really, really excellent, and typically we have a first pass yield of 100%. That's not so surprising because the technology really comes from the semiconductor industry, where extremely high quality and high yields are typically, in fact, they're just the basic requirement. Billions of wire bonds are really made every day worldwide, so this is a huge industrial process that's really very well understood. As I was saying, we have no molten phase, so we have no microstructural change inside, and because of heat effects, that's a big advantage. But we also have a bulk joint. We have no interface between the two materials that could corrode or that could get contaminated anyway. It's really corrosion proof, and that's why it easily lasts 20 years. In fact, in your regular car, you have several hundred wire bonds with this type of heavy wire that will easily last many years because of the electronic systems that are in your car. And as an additional bonus, if one of your cells fails, you can easily replace it because they are repairable. So that's the reason why, really, for e-vehicles, at least for those with the cylindrical cells, just like Tesla's, wire bonding is by far the most popular connection technology. It's also quite fast, as you saw from the videos. The typical connection speed is something like 1 second per wire, and it's relatively cheap. Depending on the volume you use, you could count on having something like a cent or so per wire connection, depending on the length of the wires and so on. But that's a good rule of thumb to use. Now, of course, there are other methods. I won't go too much into detail what's good about them and what's not so good, but resistance welding is really a classical starting technology if you start out small, because you can start with a manual entry-level solution quite easily. However, you typically always suffer from yield problems. You do need pre-made connectors. Laser welding, you've heard a lot about also in the previous presentation. It's really good for the connection quality, and it's very, very much used for high currents because you can have a much larger cross section of the connectors in laser welding. But the drawback is, again, it's quite an involved technology. The initial invest is rather high. So if you start out in this business, it can be daunting to have such a high investment. And you are much more sensible to height variations between the connectors and the cells because you're really dependent on the welding gap. You also have a thermal load because this is a real welding process with a molten phase, so you have to worry about that. Classically, you also have screw and bolt connections, which are very simple and very straightforward, but in large numbers, you don't really want to use them because the lifetime in terms of corrosion is a problem. It's also relatively costly and it takes up a lot of space. Finally, spring-loaded connections is, of course, what you know from your TV remote or any kind of battery-loaded, battery-powered typical device. They're easily repairable because you just snap out the cells and put it in. They're quite simple, but you also have a major corrosion risk, and the connection resistance over the connection will change over time. Finally, soldering, of course, you can also do that. At entry level, it's relatively simple, but it's really difficult to automate. It's quite slow, and the surface requirements are really much higher. To go a little bit further into technology, friction welding is, and what you see here is really the business end of our bonder. Friction welding is initiated by an ultrasonic oscillation in the bonding tool, very much like a standing wave here. So we need a very precisely defined resonance frequency to run all of this, but this is really our job. And once the process is all set up, then we have an extremely stable and extremely robust process that for you is just a question of switching on and switching off. There are, of course, technical requirements, to name just two of them. What can go wrong will go wrong, as Murphy would say. And what we have to worry here is that the parts have to be held quite rigidly, so the friction really works off each other. So if you have parts that are held softly, like you have these cells in a felt package on the right, the oscillation will dissipate and the connection won't be as good. Second problem that can happen is that the surfaces are contaminated with all kinds of organic or oxide contaminants, which you have to get rid of, not to kill the process. And that's typically removed by mechanical or solvent cleaning, laser treatment, or CO2 dry snow blasting, which is a process we rather like. You blast dry CO2 snow, which is very easily generated just by blasting it out of a jet. It takes less than a second per spot, and immediately you get very, very clean surfaces. You see before and after cleaning with snow. This cleaning could be done in a dry snow jet setup manually, or we could even put the snow cleaner right on the bond head, next to the bond head itself. And as you can see here on a small 16 cell assembly, we run the cleaner, here comes the jet, we run it in an optimized pattern across the surfaces. You see this works from a distance. It takes something like 12 seconds for the entire 16 cell batch, and we're done. Now, the equipment you need is what we built. We have a whole range of equipment, starting out with an automatic small series bonder to a much larger working bonder as well with automatic parts handling. And what's attractive is you can change the automation at any time. So you don't have to know what you need when you buy the machine the first round. You can add on later on at any time. And you can even put a bond tester in the machine. And that's really we are the only manufacturer who offers that. This is what the smaller machine looks like. It's a desktop machine. It has exchangeable heads for all kinds of different bond technologies, so not just for heavy wire bonding. You can also put in bond testing, even the fairly new BAM-FIT test, which I won't go into here, which is a lifetime test, and it can easily be switched. Here comes the larger machine with the batteries that can go all the way up to 500 by 700 millimeters inside the machine. Again, the bond and test heads can be exchanged, and it already has the same software as the smaller machine that we had before. Plus, it can include the CO2 cleaner, the dry snow cleaner that we just showed before. Here is the working area of the machine, so you could put many different parts in there, and or just have very large parts in there. If you need to go even bigger, of course, you can automate this retrofitable at any time, even at your site, or a customized approach. Just a short aside about bond quality, as I was mentioning before, there are two tests that are typically done, the pull test and the shear test. Both can be done on the equipment. Here is what the pull test does. It just pulls a wire up until either the wire or the connection breaks and measures the force at which this happens. This is a standard test in the semiconductor industry, which is very well established and is an excellent way to start your quality control. The second test is called a shear test. There you do not pull on the wire, you just push actually at the connection itself, and again measure the force at which it fails to give you a quality control measure. And of course, like in any quality control thing, you get a report out of this, which comes out automatically. You get a control chart, you get measurements, trends, distributions, CPK values, and so on, and also customized reports. I mentioned one more thing, and that's really that before you even get to this point of needing equipment, we can jumpstart you before the hardware. We help you with feasibility studies in getting your product defined and worked out. We can help you with prototype manufacturing, even up to small volumes that we do in contract manufacturing, to help you both get into the market or acquire new customers, and to help you, of course, with the ramp up. For all of that, we have a small brochure called Battery Bonding as a Service, which we provide on our virtual booth, and you can download that. But of course, we're just as happy to get your questions directly at the booth or at this internet site from us. And with that, I'd like to thank you very much for listening, and I'm ready for questions if you have any right now. Thank you.
Thank you also from our side, Dr. Sedmair, for this interesting speech. And I would like to start with the questions from the audience. First question is, how then control the cleanlessness after CO2 snow blasting? Anything in addition to the destructive pull or shear testing, like wettability testing?
I'm sorry, I didn't quite hear the last part of the question.
Anything in addition to the destructive pull or shear testing, like wettability testing?
Okay, yeah, we have, I mentioned very briefly, we have an additional test head that does something called BAM-FIT testing, which is an accelerated mechanical fatigue testing. I skipped that part because it's quite an involved discussion. What we can do there is we can have a quick test as to the lifetime of the wire bonds under different bonding conditions. So it's an excellent and a very novel and patented test, which only we provide at the moment, that gives you an idea of how well the process works, how well the bonding process works, and if you have any changes in bonding process, if that affects your bonding quality in that sense. So that's an additional test we would also be eager to discuss with you in detail.
Okay, so the audience is thanking for the answer, and the next question is it available for wire bonder to connect prismatic cells with 15 millimeters within or and 2.5 millimeter thickness ribbon, for example?
It depends on the cross section. If you say 2.5 millimeters thickness of a ribbon, we cannot do that with our regular wire bonder. Those would be much larger ultrasonic welding machines, and they're not used for prismatic cells because the ultrasonic energy you would need would be very high or very large amount of energy, which you cannot easily introduce into the poles of a prismatic cell because they're not rigid enough. We do bond with ribbon of about 2.5 millimeters width and I think 300 microns thickness. That's almost a standard process. The trouble is simply that it depends very much on the amount of current you need to pass. And so you need to make possibly as many as 10 bonds, at which point you slow down considerably. And then, of course, it becomes a matter of the throughput that you require.
Okay, so thanks a lot for answering the questions, and also thank you for this interesting speech. If anyone would like to go deeper in discussion or ask anything else to Dr. Sedmair, please visit the booth of FNS. They are open, they are ready, they are really welcome to answer your questions. And of course, the recording can be looked up afterwards. And if you're interested in the slides, also go to the booth and get in contact directly with Mr. Sedmair. Thank you again from our side. And we would be lucky when you join us at the next session. It will be from Lukas Buske from Plasma Treat. Thank you and goodbye.
Bye-bye.